Chapter 20, Cardiovascular Physiology, Screencast 6. In the last screencast, we actually talked about the neural control of blood pressure. Now we're actually going to talk about hormonal regulation of blood pressure, and this is how blood pressure is regulated on a long-term basis, and is primarily done by the regulation of fluid balance. So, a couple of things. We're going to come back to the renin-angiotensin system, and I'm going to walk through it briefly, but from the point of the exam, I'm going to put an impact or an emphasis on the vascular effect of hormones. These hormones also will impact fluid balance, but we're going to come back to that a little bit later, and the emphasis once again is going to be primarily on the impact that these hormones have on blood pressure, vasoconstriction, and vasodilation, not fluid balance. Now, what we'll see, basically, there are three hormones that come into play when blood pressure drops, and only one hormone that comes into play when blood pressure goes up. That says something about what the body actually prioritizes, and it takes a drop in pressure far more seriously than an increase in pressure. And if we think about it, there's an awful lot of people out there that are walking around with high blood pressure and just aren't aware of it. But you will know if you have low blood pressure because it's going to be symptomatic or something along those lines. Now, the primary hormonal system that comes into play when pressure drops is going to be the renin-angiotensin system. What's going to happen here is we have the liver, which is producing this inactive protein known as angiotensinogen, and this will be released into the blood. Now, depending upon what's happening to blood pressure, we are actually going to see the kidneys release renin. The signal for this will either be a drop in blood pressure or an increase in sympathetic activity. Now, renin is going to take this inactive protein, angiotensinogen, and it's going to convert it to angiotensin 1. This occurs within the blood. The thing to remember here is angiotensin 1 is still inactive. To activate or convert angiotensin 1 into the active form angiotensin 2, you actually require an enzyme called ACE, or angiotensin converting enzyme. I know this is a lot, and we're going to come back to this, and as I said, we're going to put an emphasis on the vascular contribution of what these hormones do. So now, when we look at angiotensin 2, the important thing to remember here is angiotensin 2 is a very active, powerful vasoconstrictor that will increase resistance. Now it's going to do other things, but we're not going to focus on that right now. So what you're responsible for as far as angiotensin 2 goes, it increases blood pressure because it's a vasoconstrictor. We will come back to the impact that angiotensin 2 has on blood volume, urine formation, and so on at a later date. But here, let's actually walk through the pathway. So the kidneys are going to detect either a drop in blood pressure, notice it comes into play for a drop in pressure, or an increase in sympathetic activity. Angiotensinogen, which is inactive, is being produced by the liver. Once pressure drops, or we actually look at the sympathetic activity, renin is going to convert angiotensinogen into angiotensin 1, and this is still inactive. It's going to be ACE, or angiotensin converting enzyme, which is eventually going to convert angiotensin 1 to angiotensin 2, and the thing that we have to remember here, this is the active form. And the impact that angiotensin 2 has on blood pressure is it is a very, very potent vasoconstrictor. That's very important, and we want to keep that in mind. We are not going to discuss at this point in time the impact it has on fluid balance, which is more of a long-term regulation of blood pressure. So the other thing that we're going to look at is aldosterone. And when we talk about aldosterone, we're not going to spend a lot of time addressing this now. It really does not have a significant impact on vasoconstriction or anything having to do with blood vessels. So we're going to come back to this because it's a much greater player when we're talking about regulation of blood pressure through fluid balance. Now, antidiuretic hormone, or ADH, this is something that will help maintain or increase blood pressure. Remember, this is a hormone that's coming from the posterior pituitary, and it's going to be stimulated by an increase in solute concentration, or angiotensin II. Okay? Now, a drop in pressure will also cause a release in angiotensin II, in ADH, but the primary stimulus for the release of ADH is going to be an increase in plasma solute concentration. Now, the primary effect of ADH is going to be on the kidneys, but we really don't want to talk about that right now. We are concerned with ADH because what it does when it is released in large amounts, it is going to cause vasoconstriction and it's going to increase resistance. This is the reason why another name for ADH is vasopressin. So the two hormones that come into play that have an impact on blood vessels when blood pressure drops are going to be angiotensin II and ADH. That's an important thing to keep in mind, okay? Now, when we look at atrial natriuretic peptide, this is the only hormonal mechanism the body has that comes into play when blood pressure increases. And it increases for a very specific reason, and that specific reason is an increase in blood volume. So what happens now, this hormone will be released from the atria of the heart when the walls of the atria are stretched because of high blood volume. Now, this is actually going to stimulate vasodilation, so we have a decrease in peripheral resistance. That is the impact it has on blood vessels and helps to decrease blood pressure when it's high. It also does a lot having to do with fluid balance, and we're going to come back to that for the most part when we're looking at that. Now, when we're looking at some clinical situations that are tied into blood pressure, the two of concern are going to be high blood pressure, hypertension, or hypotension, low blood pressure. When we look at high blood pressure, this is a chronic condition, and generally, full-blown hypertension is described as systolic blood pressure greater than 140 millimeters of mercury and or diastolic greater than 90. So notice the and or. They both do not have to be elevated. Only one of them has to be elevated to diagnose hypertension. The problem here is the impact on what this high pressure does to the wall of the vessels. Remember, one of the biggest issues that promotes atherosclerosis is response to injury of the inner lining of the vessel. So this is what we start to see here. So then we might have thickening of arterial walls, arteriosclerosis, and this is one of the biggest causes of heart failure. Now, hypotension is low blood pressure. Now, this is a chronically low blood pressure. The important thing to remember here is you want pressure to be as low as possible as long as it's not symptomatic. And when we look at the symptoms, we're talking about fatigue, dizziness, and fainting. Now, hypotension is when we have a chronically low systolic pressure less than 90 and or diastolic less than 60. Now, this is going to be described as hypotension. If you have low blood pressure but you're not symptomatic, that's not an issue at all, and it's a good thing. Now, one thing that many people experience is what we refer to as orthostatic hypotension. This is when blood pressure drops after sudden standing. This is going to be accompanied by dizziness, lightheadedness, and fainting. And basically what's happening here, your baroreceptor reflex is not jumping in fast enough to counteract this change in posture, resulting in blood pressure dropping. Now, a couple of things we want to keep in mind here. This is the last topic of this chapter, and it's the distribution of blood during exercise. Now, one of the things that's going to happen, and I hope this makes sense, is we're going to see an increase in total blood flow or cardiac output during exercise to meet the demands of exercise. This is basically going to result in your heart beating stronger and faster. Blood is going to be moved from our venous reservoirs. blood is going to be redistributed so that it goes to active tissues as opposed to inactive tissues. So if we look at some things to expect, we're going to see an increase in flow to coronary vessels. So heart walls are getting more oxygen. The blood flow to skeletal muscle, that's going to increase drastically to meet the muscle's metabolic demands. We're going to see an increase in flow to the skin because that's going to help us dissipate the heat that is associated with an increased metabolism. We're going to see less blood going to the abdomen, organs of digestion. We're also going to see less blood flow going to the kidneys. And that's just to maintain blood volume and pressure. So let's take a look at what's happening and comparison distribution at rest to distribution during strenuous exercise. So if we look at cardiac output at rest, we're looking at about a little over 5 liters compared to exercise when it's over 17 liters per minute. So if we look at the brain, okay, typically at rest, it's a little bit more than half a liter. If we look at the heart, it's about a quarter of a liter, skin, a little bit under half, and then a little bit over a liter of blood flow going to skeletal muscle. If we look at the kidney and abdominal organs, we have a greater blood flow going there. So to the kidneys, typically a little bit over a liter, and to abdominal organs, a little bit less than 1.5 liters. Look at the big difference during exercise. One thing that we keep constant is going to be blood flow to the brain. No real difference in demand, okay, if we're looking at brain activity going from rest to exercise. But look what's happening to the heart, the skin, especially skeletal muscle. So now, if we look at the heart, we're now looking at blood flow approximating 750 mils per minute, so about 3/4 of a liter. If we look at skin, okay, that's now just under 2 liters per minute. If we go to skeletal muscle, it's going from a little over 1 to 12.5 liters per minute. That is significant. Whereas areas that we're going to see decrease is going to be the kidneys. We're now down to a little bit over half a liter. And then if we look at the abdominal organs, we're now looking at 600 mils, just a little bit over half a liter. This is a dramatic drop. So what's happening during exercise, we basically are increasing flow to working areas, and it's coming from areas that aren't really necessary or active during strenuous exercise. So it really is kind of important to understand what's happening with respect to how blood flow changes during rest to exercise.